Okay, today we're looking at equilibrium problems and looking at specifically that of a seesaw. And what we'd like to know is where to place a fulcrum in order to achieve static equilibrium. Now to do this, we have to do a few things. First of all, we need to know what the mass of the plank that makes up our seesaw is, and also how long is it. And so to do that, we have to make sure we use the scale that is provided. So every 2 segments that's on the graph paper is half a meter, and also it's going to represent half a kilogram in mass for the actual plank. And every block is going to represent 1 kilogram. Okay, so let's get to solving this. First step is I'm going to use a ruler to figure out how many squares I've got, because it turns out they're equally spaced. And so I've got one set of 2, and then I have looks like 9 sets of those 2. So that means our total length would be 4.5, because 0.5 times 9. And our total mass would be 4.5 as well, because that's 0.5 times 9. Now the center of mass for this would be right there in the center at 4.5. Well, 4.5 is popping up a lot. So let's go ahead and take a look at what would our next step be. And of course, there's the information. We label them mass 1 and mass 2. We want to kind of start getting a feeling for how to label things so we could actually start to do our drawing. Our next step is to make a very simplified drawing of the plank. No masses on it, just some arrows for the forces. And again, we don't know where to put the fulcrum, but I'm going to say that the fulcrum is going to be on this side. And at this point, I'm thinking physics. I'm thinking, okay, there is 6 kilograms over here, and there is 4.5 over there, actually right here, and there's 4 right there. So there is more mass on this side, but I also know that the distance times the force is what the torque's going to be. So in order to balance the torques out, I'm going to have to put the fulcrum somewhere, and I'm thinking over here, because I'm feeling like if I give this too much of a torque arm, it will out-torque those other sides. And if I move this past that center of mass, it's going to also allow the plank to also help this 6 kilogram mass out-torque that 4 kilogram mass. So there's my reasoning. I want to make sure I pick a place that makes physical sense and I won't wind up causing problems later on. So again, my choice of fulcrum is going to be on the left side of the center of mass, simply because of the way the masses are distributed. Now, let's go on. I want to make a simplified drawing. I want to draw every force, include the fulcrum, just for the purposes of measurement. And so I will draw arrows that represents all the forces that are acting on the plank. And I'll also want to draw the distances from those arrows to the fulcrum point, or where the upward force is. Now, I also need to have some labels on here because I'm going to need to use these later for doing algebra. So let's go ahead and do the next step, which is labeling everything. Now, first of all, the force that's supporting upward is the normal force. The first force that I encountered, that 6 kilogram mass, that's a M1 times G. I label that M1. I call this the mass of the plank times G. Of course, that's the weight of the plank. And then I call that M2 times G, which is, of course, that 4 kilogram mass on the right-hand side. Now, as far as distances, I don't know. I know that my total length is 4.5, but I don't know what my X would be, where the fulcrum's located. So what I'm going to do is I'm going to say, well, from the left side over to the fulcrum, that's X, which means, seeing how it's not quite to the center of mass, and the center of mass happens at L over 2, then the plank's lever arm is actually L over 2, or half the length, minus X. And the length for the far right mass would be L minus X, okay? And that's basically setting up my lengths and labeling them. And this is a very crucial step, because once you have this, you're going to go on to the next step, which is applying physics concepts. Now, the physics concepts at hand here is we're trying to achieve static equilibrium conditions. The first condition is that of keeping the net force equal to 0. That means that the normal force provided by the fulcrum has to equal all the weights pulled down by the plank and the 2 weights on either end. Now, the next condition is the one that we're really going to focus on, because it's the condition that says the net torque has to be equal to 0. And reminder, torque is the force times the lever arm. Actually, I should make a correction. It's the perpendicular force times the lever arm. Now, in this particular case, these forces are perpendicular to our lever arm, so we don't have to worry about finding the sign of this or the sign of that. So we're pretty good there. So let's go ahead and start filling out the equation. Now, the sum of forces, pretty simple. That force plus all these other forces added together minus. Actually, there should be parentheses around this because this all has to be grouped together. So there's a mistake I made. I needed to put parentheses around these weights because otherwise I would subtract the first one and then we'd add all these others and it would be off. We'd actually not equal 0. So on yours, make sure to put parentheses around here. Luckily, it's not going to influence the rest of the problem that I made that mistake there. So let's go on. The next equation is basically the torque equation, which is basically saying this length times this force to find the torque, the lever arm times the force applied. Now, this first torque we see, because it's rotating the object, if it could rotate, in a counterclockwise direction, is a positive one. Now, on the other torques, for example, the torque provided by the plank, that's going to rotate clockwise, which makes it a negative torque. Now, the other one would be also causing a counterclockwise rotation, so that weight on the right side would cause a negative torque as well. So there's the equation for the net torque, and all of it should equal 0. Now, the next step is not to put numbers in. I know you want to. I know it's a compulsion you have, but don't. Avoid the numbers. They can clutter up what's going to happen next, which is the algebra. So we need to do algebraic manipulations. Now remember, the order of operations are important, and in fact when you're trying to undo something, you may need to do the order of operations backwards. But let's take a look at this problem. We're focusing only on the net torque, because the net force really won't help us solve what we're looking for, which is the distances, which is related to torque. So the first algebraic thing I'm going to do is distribute these terms through these parentheses. When I do that, I need to remember to make sure that negative goes into that negative and makes a positive on both of these terms. Next, I basically want to group like terms. And when I mean like terms, I mean the same L's on one side and X's on the other side, so that way I can isolate what X is. Next, I want to remove the common terms and factor them out. Now you notice how there's an X and a G in every term in here, and a G and a L in every term in here. So I want to factor those two things out and leave a parentheses behind with everything that was left behind. Now the next thing to notice is there is a G on both sides of the equation. That means I can go ahead and divide G out of the equation, which leaves me with X with M1 plus M of the plank in the M2, and L times M2 plus M of the plank divided by 2. And the last step would be just to divide by all the sum of the masses on the left side on the other side, the right side. And what we wind up with is an equation for X. Now at this point, we are ready for numbers. So now's when the numbers can come in. So we make the list of numbers. We have L equals 4.5 meters. And that was from the interpreting the graph. And the mass of the plank, again from interpreting the graph, was 4.5 kilograms. The mass 1 was 6 kilograms, mass 2 was 4 kilograms, which then allows us to plug the numbers into the equation we have. And we wind up with this, well, it's just a filled out equation that we need to use a calculator on. So let's use a calculator. Now, basically what I want to do is I want to put it in just like it is here, but without any of course, the, let's clear that up, without any of the units on there. And this takes me forever. Oops. Especially when I make mistakes. So when I do all that calculation, and I'm sorry for it taking me so long, we get 1.93. So our answer we wind up getting Is 1.93 big lot of numbers, but the reality is we want to go with a smaller amount of numbers because we don't have that many significant digits. So the answer is basically it's x equals 1.9 meters from the left side of the plank. Now I have to put on there from the left side of the plank because it's not 1.9 meters from the center mass or from the right side. It's specifically from the left side of the plank, which means our fulcrum is located right at that location. Now, if I had chosen the wrong location to place my fulcrum, if I had thought about the physics wrong, then what would have happened was I would have had a problem with my numbers. They would have come out and made no sense. So if that occurs, you may want to go back and look at how you originally set up the problem, especially if you looked at your algebra and know you did everything right. So that's how you work that kind of problem. And so we'll be moving on to the next one in the next video, but good luck.